All right, so allow me to say at the beginning that this presentation is really a request for help, and you'll understand that as I move through it, and particularly at the end. But first, the background that I presented in the opening remarks, I'm an application developer. I'm on an application development team, and we're not tool developers, and we're not ontology developers and knowledge coders. We really depend on those folks to use the tools, to give us the tools and the ontologies to develop our applications. So what I want to talk to you about is one of those today, the use case that we've been working on for quite some time. And that use case is an application to automate equipment, and specifically agricultural equipment. So before I describe the equipment, let me define the domain, the information that we're dealing with as it relates to that automation project. First of all, it's place information, location information. Where am I, and what do I know about that location? The second part of it is the biochemistry of what I'm dealing with. That could be things such as protective chemicals that are being used to protect plants, pesticides, nutrition, vaccines, chemicals like that. The third set of domain information that we're looking at are threats to the food supply: inadequate moisture, inadequate nutrition, bacteria, insects, viruses, things like that. And then finally, the mechanization aspect of this thing would be equipment that many of us are familiar with conceptually, things like tillers, sprayers, harvesters. So that's the domain of information that we're dealing with. So what is our objective? One is to create this automated device, and think about this to start with as a sprayer. What's a sprayer? It's a device that delivers a chemical solution to crops. So what we want to do is to develop an intelligent sprayer. Now, what would that do? The first thing it would do is it would read electronic instructions from a very technical document that goes by the code word Material Safety Data Sheet. This is one of the more complex expressions of components and mixtures that you'll find, in the wild. It's if you look at these material safety data sheets, they are just amazingly complex. The second is it's going to read information from sensors, data about biological threats or the environmental conditions that are associated with that place. Third, that sprayer is going to have to compose and formulate a chemical based on sensor data in real time. And then fourth, it's going to have to deliver that at a specific location. So think of that as basically being a machine on a map applying a configuration according to the sensor information that has been reading. So to date, we have made considerable progress in being able to accomplish that. And I'll just itemize some of the working components that we've got under our control. I've shared examples of this with Marco separately, and I'm certainly happy to put those back into the community so that you can see examples of what I'm talking about today. They wouldn't work very well online because they're fairly complex. They're even more, they're less interesting to look at than scenes in Amsterdam, let's put it that way. So one of the elements that we had to develop was a soil ontology. What is soil and where is that soil located? Now in the United States, we haven't done this elsewhere. We have that soil on a GeoJSON map defined in 3 foot by 3 foot by 3 foot cubes. So the pixel for the information about the soil we have is highly granular. We also have extensive information for those pixels about soil chemistry. Now that chemistry is based on 2 data sets. The first is the CHEBI data set, Chemical Entities of Biological Significance, that comes out of the EMBL organization. And in the US, it's based on the PubChem database. We also have a great deal of information about atmospheric chemistry. And here are 2 core ontologies, are the Erster core ontology and a subset of SWEET, which is the Semantic Web Earth Environment terminology. For atmospheric chemistry, here again, only in the US, we have that by time. So it's the intersection of space, where are we, and time, because time is going to tell us what the growing seasons are and what the conditions are that are inputs, obviously, to the sensors. Also by place, we have biologics. That's the microbiology of the place where we are delivering this for example, sprayer content. And we also have good information about insects and the entomology of that space. We depend heavily on the plant ontology, which is a very extensive ontology developed a number of years ago. And we have very good information about the growth conditions by species and variety at that place, and information about the threats. On the sensor side, we use the sensor ontology, and up until now, we've been using sample sensor data to model our environments. So that's what we have. So now what I'm going to do is traverse from the practical to the theoretical. And herein lies the problem. What we don't have are real sensors that produce the desired results. Those sensors are simply not commercially available. So here we have a dependency that says, well, we've got this idea and we can mock up our data to prove that the idea conceptually makes sense, but we don't have the sensors that we can work with that actually produce the real-time data that we can operate on. We also don't have the machinery that we can automate. So the machinery is going to be staging the components, mixing the components, applying the components, and most significantly, error handling. Because just like in firefighting, if you're in the middle of a burning building and you lose connectivity, you're in a world of hurt. And while the problems are not as mortal as they would be in our first presentation, when you lose connectivity in an environment that we're trying to work in, obviously things come to a dead halt, and that's an outstanding failure. Now, what do we have to work with? We have the ISO 11783 specification for tractors and machineries. This is sometimes called the ISO bus, and it is simply the specification for all of the equipment that constitutes farm machinery. Now that has been specified in an XML XSD format, and that's principally focused on the units of measures that each one of these components use. There is good information about the interconnectivity of these components. And so what we had to do was to take that information and reconstruct it as an ontology, which we have successfully done, and we've pretty well defined that approximately 340 components that are defined in that specification and re-engineered them, if you will, into an ontology that we can integrate with our other ontologies. And one of the principal ontologies that we're using, I haven't mentioned so far, is AgroRDF, which is, think of it as basically being an ontology that defines the dimensions of an agricultural installation. So we've been able to pull these things together, once again, conceptually, but not mechanically. So what do we need to do next? And using the vernacular, what we need to do is basically build a subset of a Tesla, and without having to build a Tesla or without having to build a gigafactory. We need to come up with some way where we can take the components of what we have working in software and implement them so that they can be visualized in a simulator. Because we're dealing with an audience which is highly skeptical. The agricultural community actually is one of the advanced technology adopters, but these are people that are practical and they understand the real world conditions that can interrupt theory, and they're a very skeptical group. And until they understand how something is going to work and they can see it in action, they're disinclined to believe or trust the promises made by vendors like us. So we need to have a simulation environment that permits them to visualize how this is all going to work and to give them some confidence that the process of moving from theory to mechanization actually is practical. Now, the delivery of this must be done from our perspective on an open platform. And here is the simple reason why. This is an industry which has large capital expenditures. And those capital expenditures are often vendor specific. And many of us have heard, and this is particularly true in Norway and some other places in Europe, about the right to repair movement. The technology we have has become so complex that the vendor claims only they are able to make changes and repairs to the equipment. And we all know that in software development as being a lock-in. And that lock-in is in spades in the agricultural industry. And it's an acute financial problem whereby people make very large investments but are unable to maintain their equipment because it's not open, it doesn't conform to a set of standards, it's not interoperable. So we think the economic issues associated with this industry around the right to repair are one of the compelling reasons why people will pay attention. And if we can come up with a method by which they can visualize how this will all work in a simulated environment, we think that we can go to market and enlist partners that contribute to the implementation of the various types of equipment that are necessary to run in an agricultural environment using interconnected intelligent machines. So this has been a 10-mile journey for us, and we started by shuffling forward on our knees. Believe me, this has been a bootstrapped operation. It's been very painful. We think we have most of the building blocks. We think we're approaching the last mile of this exercise. We think we've solved about 80% of the problems, but the reality is probably that we've got 80% of the work in front of us. But we're fairly optimistic that we've taken this thing to a point where that if we had this in simulator environment, we could demonstrate the activation of ontology-based specifications, have a shackle environment, which are the constraints that are controlling the methods by which these machines have to interoperate, and then would be able to generate and support a realistic sensor-based community where the sensing devices will increasingly be tuned to play nice and integrate with this this ISO-bus connected type of environment that we're looking at. So our need and what's missing in the next steps in this exercise is the ability to simulate an ontology-based, shackle-based, sensor-based environment so that people can visualize practically how this thing would work. So Marco, that's our request for help from your group.
Thank you very
and from
much.
others about helping us get this this project up to the next step.
Thank you very much, Jay. I'd like to take maybe 1 or 2 questions from the audience. We have a few agriculture people here. Maybe they have a question for you.
I was interested in Monaco, if she's still online.
Monica is definitely would be the person to speak to. I remember someone approached me in 2011 in New York, and they wanted to hire me. I remember that it was called the Weather Bill. Do you remember these guys?
I'm not familiar, no.
Yeah, there were 2 Google guys, and they started to work in the. So leads me to my question. So what is the current state of affairs? Like, is that market basically owned by a few companies? Do you have to buy in the data currently? Is this difficult?
The market is dominated by integrated machines. So the largest manufacturers, harvesters, John Deere, people like that, definitely own the market. And the reason for that is because they are the purveyors of the largest piece of equipment in this exercise. So if you will, their tractors pull, pardon the pun, a great deal of business in the form of the connected devices. But in some ways, this is the last instance of IBM mainframes in the world. If you bought into CICS, IMS, or DB2, SNA, IBM had turnkey solutions, and they worked. And that property is dominant, still dominates the agricultural market to a significant degree around the world. And we're hoping that something along the lines of what I'm describing today is going to open that a little bit. We think that the opportunity is going to come with the interchangeability of specialized devices that are very sensitive about crop harvesting, when to select something and when not to based on growth cycles, that are very selective about treating microbiology conditions, fungus, bacteria, applying moisture where it's needed, not where it's needed, things that you can imagine that are sensor based, where the sensor has to detect biochemistry, has to detect the various other dimensions that go into making a decision, and then where that information is applied by a specialized device. That vision does not, has not taken hold in the target market.
Okay, so let's see if we can, maybe Monica.
Yeah, hi Jay. So I was wondering, have you looked at some of the specifications from Ag Gateway?
I'm aware of it, but to the degree that we are aware of that, we are aware of AgroRDF and the implementation of Ag Gateway, the ISO 11783 version of that, which is an XML-based version. That's the extent to which we are familiar with what you're asking.
Yeah, and actually we've been talking to Ag Gateway for the last 3 months about RDFizing their UML specification.
Yes,
and
that's what we had to do ourselves, right?
We've been doing that ourselves within.
Okay.
Yeah.
How about that?
And we
both saw the same problem.
Well, our focus at the moment is mostly plant protection products. So we are looking at representing, pesticides and the labeling around it and the packaging around it and all of those sorts of things. And although Ag Gateway has some sort of a UML representation, but we are working together with Wageningen University and Ag Gateway on producing a more or less comprehensive and consolidated model here. And actually, we have something. We have something ready, and I think in a week or two we are going to pitch that to Ag Gateway. But we haven't started work on sort of the sensor related stuff that you're talking about. But also, have you thought about using the SOSA, the new Semantic Sensor Network Ontology?
Yes, we actually do use that. That gives us the ability to specify the devices that we want to speak to. The problem is, it's the domain problem, and that is, what are they sensing? Do they understand the presence of different type of fungus or different type of microorganisms? And there we have to, no work has, to our knowledge, has really materialized in that space. So there has to be a need for that. In other words, if you're trying to sense the presence of something, you have to do something about it, right? You have to apply some solution to it. And it's the chicken or the egg problem. The sensor people are not going to actually develop the intelligence about detecting microorganisms until some mechanization can apply a solution to protect the plant. So it's that round robin problem that all of us, all innovators face. How do you get somebody to take that?
It's a domain-specific modeling issue. You only model the very minute details of the domain you're interested in. Maybe we can have a conversation offline. Yeah. I don't want to take too much time here because...
Very good. No, it looks like you two found each other. That's great. So maybe we have a bit more of that later on in the discussion. And there was Klaus. Did you have a quick question?
Yeah, very short question, goes in the same direction, because you mentioned that you use PO, and I'm, as I said, I'm not exactly from the agroscience domain, but from biodiversity. But as far as I know, this Aggrovac vocabulary, which is Thesaurus, I think, is very much covering in the agroscience domain. How well does the different Ontology align with that, and did your techniques apply to get this Aggrovac vocabulary, which is an ESCOS, I think, so somehow mapped to the ontologies, or is this a problem that everything is in Aggrovac as it looks from my outside perspective?
Okay, so we're intimately familiar with the technologies you're mentioning. I'm happy to talk in detail offline, but let me summarize for you. Aggrovac is one of the more sophisticated, arguably Aggrovac, coming to the United Nations Food and Agriculture Organization, was one of the early implementations of an ontology. So they early on used the SCOS ontology, the simple knowledge object sharing environment, to encode information that previously had been in Agris. So that's how Aggrovac came about. And it is a very sophisticated specification language for various aspects of a wide variety of things, from human nutrition to agriculture, etc. That Aggrovac is closely related in the United States to the National Agricultural Library Thesaurus. We actually have the maps between those two so we can go from one to the other. At the detail level, we know exactly what the specification means in either one of those two vocabularies. The second aspect of Aggrovac that's extremely important, and this is where UN really pushed the envelope, is the Aggroentology, which are the verbs which allow you to build linked statements. Because up until then, Aggrovac was really nouns. It was not the verbs. It was the implementation of Aggroentology that really gave power to Aggrovac. And today, when you look at Agris and Aggrovac, it is one of the most impressive implementations of linked data in the world. The two most impressions, hands down, are Wikidata and Agris. Now, to that, you have to complement it, and that's our approach. We've used different other ontologies. The plantology, for example, is very comprehensive with regard to the parts of the plants, of different plants. None of that information is in Aggrovac, very little. So we have to extend our knowledge about our target domains, and the plant ontology was absolutely essential to being able to characterize the crop domain. Then you have another issue, and I won't go into any more detail now, and that is, what is the growth cycle? Because you have to be able, in this world that we envision, selectively harvest. You may harvest 2 or 3 times, and you need to be able to intelligently select something that's ready for harvest and allow the thing that's not to continue to grow. That means that you've got to integrate a harvest-oriented or plant maturity ontology with this environment so that the sensor can determine what the plant maturity is before it takes the next step. Okay, I've probably gone into too much detail.
I think very good. I think it looks like we have a very interactive discussion already. So thank you very much again, Jay. There's